Hey, welcome. So in this lecture we're going to look at incompressible flow again. I'm going to try and understand in a more rigorous and general way why divergence of u is zero for small flow speeds compared to the sound speed. So in the previous lecture I looked at this in the more physical arguments and a simple one-dimensional steady-state cases. This is not the full rigor that you might find in a mathematical treatment, but I'll try and give you an introduction and a flavour for what it involves. So the first idea is to introduce normalization, and so we're normalizing the equations, and this means that we're taking out the dimensions, so we're taking out the units. And we're trying to make all the quantities in the equations of the same size, so all of order 1. So this is removing dimensions. So things will no longer have dimensions of meters or seconds, but they'll have no dimensions, and there'll be typical length and time scales, and factors will appear which depend on them. And we'll see why this gives us quite a powerful way of looking at equations and understanding which terms are small, which terms are large. So we'll start by looking at, say, the density equations. So in Euler's equation, we have d rho by dt plus divergence of rho u is equal to 0. And so here we have a bunch of different quantities. You have the density, you have the time, we have lengths, which are, say, in meters, time in seconds, rho is in this per particle mass per cubic meter, and u in meters per second, for example. And so to get rid of the dimensions, what we're going to do is we're going to choose typical scales. So we choose typical scales, and so rho, for example, becomes a typical scale. We're going to call it rho naught, multiplied by a normalized quantity. And so rho naught has units of kilograms per cubic meter, for example, the same as rho does. And now rho hat has no dimensions. It's a quantity, a number. It's just a number which is of order 1. This just means it's around 1. We just choose rho naught, say, as the maximum density, and then this is up to 1. But this is the idea. This is no longer 5 10 to the 20 particles per cubic meter or 3 kilograms per cubic meter. This is now roughly 1. It's just a number. And so we do the same thing for the other quantities. So u becomes u naught. It's just a number, but it gives a scale. So this has units of meters per second, for example. And then u with a hat is a normalized velocity, which has no units, but it's of order 1. And so we can put these into this equation. Slightly more tricky ones are say the scale lengths. So if we have a gradient, for example, this is just a d by dx. This is just like a derivative, and so you can write this is basically 1 over a length scale multiplied by a normalized derivative. And again, this is now expected to be of order 1, and this gives our units. And so we put these into this equation. You see we've missed out time, but I'll come back to that one and show how that comes out. So we have d rho hat, and this brings out a rho naught. So rho naught is just constant, so it comes through the derivative. Then we have t, which we've left as seconds currently. So we have rho hat. We're going to normalize all these things, so I'll just put hats in here. And now the rho hat, the gradient brought out a 1 over length. Here we have a rho naught, and here we have a u naught. And so you can see now, so this whole thing is equal to 0. So you can see you have a rho naught on both sides, so that we can just cancel out. Then we have a u naught divided by L, and this can be absorbed into this time. So we can just say that the time, the typical time scale is just the length scale divided by the typical speed. So it makes sense if you have a typical length and you have typical speeds, the kind of times that the density will evolve on is this length divided by the speed. And so d by dt just becomes u naught over L and cancels out these terms here. And so we just have that d rho hat or dt hat, which is now this is now the dimensionless normalized time. Rho hat u hat equals 0. So now I have the same equation, it's just that this is now dimensionless. And what this has told us is the typical timescale. So we now have a consistent timescale for the evolution, combined with typical length scales for the derivatives, speeds, and densities. And so now we can put this into the second equation. So take the momentum equation. Momentum equation. So we have du by dt. So I'll just write out the original equation here, plus u dot grad u. 1 over rho was the mass density gradient of pressure. And so now we need another quantity, so we're going to say that pressure is again a typical pressure times a normalized pressure, which is of order 1. And so now we can put all these quantities in here. So we have, so again, u gives us u naught. 1 over t gives us another u naught for L. And now we have a u hat over dt hat, so that's that normalized. If you look at this expression here, these are going to give the same factors. So we have u naught, another u naught, and a 1 over length. And so this quantity here, we'll just put in brackets. And here I'll just put u hat dot grad. Just save a bit of writing. So these factors just come out as being the same. Now on this side we have a 1 over rho, so we have a 1 over rho naught, rho hat. We have a 1 over length from the gradient, and then we have this p naught factor here. So we have a p naught, and then here we have a grad hat, p hat. Okay, so some factors here will cancel out. So we have a length, particularly on this side, we have a length here that can cancel. And this is starting to look a bit like the sound speed. So we have p naught divided by rho naught. So p naught rho naught is just the sound speed squared divided by gamma. Because gamma p over rho is sound speed squared. And so now we have, over here we have a 1 over rho hat, so with a minus sign here. We have sound speed squared, and here we have u naught squared. And so we're going to take the sound speed over to this side and get Mach number. So we have u naught squared from here. We have a sound speed squared coming from here. And we have a gamma factor here, which will just move over to here. And that whole thing multiplied by this, so du hat by du by dt hat. I'll just copy this, dot grad u hat. That's just the same as this. And then equal to this bit here. So we have a minus 1 over rho hat p hat. Okay. So all the quantities with hats we've chosen so that they are all of order 1. And yet what this is saying is that this is the Mach number squared. So Mach number m is just u naught over cs, so it's the ratio of the flow speed to the sound speed. And what this is saying is that as the flow speed gets small, so this Mach number gets small, this whole left hand side will get small, and so the gradient of the pressure will get small. So as Mach number gets to 0, basic gradient of pressure will go to 0 because this rho is of order 1. So the only thing that can get small here is the gradient of pressure. And this is showing what we've seen earlier from just looking at the Euler equations, that when divergences are small, we would expect the pressure gradients to be small, so that as the flow moves, the pressure is constant and the density constant as well. And this is just showing a bit more rigorously how much the pressure is changing, and it depends on this Mach number squared. And so now to start to put this into the pressure equation. But to do that, we need to understand why the gradient of the pressure of p hat is going to 0 when p hat we've chosen to be order 1. So the way that we can resolve this is by saying that p hat, which is of order 1, is a combination of two things. It's a constant background pressure, which I'm going to call p bar, and this is of order 1 because we've chosen p to be of order 1. So p hat is p bar, which is a constant, plus a perturbation, so the ripples on top of the pressure, so say sound waves, which depends on the Mach number. We call this P1 hat. So this is a perturbation. And then you could essentially extend this to m squared P2 hat plus m cubed. So you could essentially do a Taylor expansion in small parameter, where the small parameter is the Mach number. So here we assume that m is small, and so we can do a kind of expansion in m. And so you can substitute this into the pressure equation. So pressure. So here we have dp by dt plus u dot grad p. And then this is equal to minus gamma p divergence of u. That's the original equation from Arnold's equation. I'm going to substitute in all these pressures and the normalization factors we had before. And what we'll see, of course, that all the other normalization factors cancel out, and we're just going to end up with an expression for this divergence. So as before, t just gives us a u naught over L. We get the same factor from here, this u naught and 1 over L. P is being differentiated in time, and so if this p bar is constant, then we can write that d by dt of p hat is just, this is 0, this doesn't change in time, and here we get a Mach number factor coming out, so it's dp1 by dt. And here we have the same for gradients in space. So p bar is constant, and so any gradients in space only act on this part. And so we have gradient of p hat. It's just Mach number dp1 grad. Apologies. Grad p1 hat. Again, we've chosen these so that P1 is of order 1, P2 is of order 1, P3, and so on. So Mach number here is the small value, and P1 is of order 1. And so again, all the quantities in this equation are going to be of order 1, and so we look at the magnitudes of the different terms. So going back to here, we have this 1 over t gives us u naught over L. This d by dt first gives us a p naught factor, because we're converting from say SI units into dimensionless quantities. We get a Mach number factor from this, and here we're left with dp hat 1 by dt hat. And then the same thing happens here. So you have a u naught over L, p naught from normalizing this, and then a Mach number because we have a gradient of p. So here we just have u hat dot grad p 1 hat. And now on the right hand side we have minus gamma p naught p hat, and then we have here the L naught, so 1 over L and a u naught, so a u naught over L dot u hat. Apologies, I haven't run out of space here. So most of these factors again will cancel. So you have u naught over L, and that cancels out. So u naught over L. You have a p naught, so cancel out. And what we end up with is this factor Mach number multiplying this quantity here, so dp1 by dt plus u hat dot grad p1 hat. These are all normalized too. So it's just exactly the same factor here. Is minus gamma p hat dot u hat. And now all these quantities, so p hat is order 1, u hat is order 1, and now as Mach number gets small, this left hand side goes to 0. So as Mach number goes to 0, because this is of order 1, we must have the divergence of u also goes to 0. So if you have slow speeds, slow flow speeds, then the divergence of the speed goes to 0. Now, a slightly more rigorous way of showing this, you can essentially move this m over to this side and do what's called a singular limit expansion, and that will provide a more rigorous proof that velocity isn't just going to zero here. So if you want to look at more details, look up singular limits